Hello, this is a walkthrough of my final project for CSCI E90. The goal of this project was to build an event-driven log sanitization and security alerting pipeline on top of various Amazon Web Services. Accidental logging of sensitive data is a real security problem. Examples include things like passwords, API keys, credentials, and credit card information getting stored in log files. The goal here was to prevent sensitive data from being written to long-term logs while still allowing secure analytics and alerting to take place. In other words, we want to sanitize logs before they get committed to long-term storage. In addition, we also want to provide timely alerts whenever serious security events occur. At a high level, this is an event-driven pipeline built entirely with AWS managed services. It begins with a Python script that writes fake application log data into Amazon CloudWatch log groups. From there, a CloudWatch logs subscription filter streams every log event into an AWS Lambda function. The Lambda function is the core of the system. It detects personally identifiable information via regular expression pattern matching, sanitizes sensitive data, assigns a severity level to each event, and then takes multiple steps. First, it writes both the sanitized and the raw logs to Amazon S3 buckets. If a log event is classified as high or critical in severity, the Lambda function sends an alert using Amazon SNS. It also writes information back to Amazon CloudWatch for further monitoring and evaluation of the function itself. For analysis, sanitized logs are cataloged with AWS Glue, queried with Amazon Athena, and then visualized in Amazon QuickSuite. It should be noted that all information stored in the S3 buckets is encrypted with a symmetric key from Amazon Key Management Services. And in addition, Amazon Identity and Access Management is used throughout the application to ensure the concept of least privilege. In order to start the pipeline flowing, we have a Python log generator. This script simulates application behavior by writing logs directly to AWS CloudWatch. It generates a mix of normal and intentionally dirty logs. The dirty logs are designed to leak sensitive data such as plain text passwords, AWS-style access keys, and credit card numbers. This allows us to validate that the sanitization logic and alerting behavior are working as expected. After importing some libraries, we provide the script configuration parameters to point it to our AWS CloudWatch. The script currently generates 10 events at a time, with 25% of those being incidents. We have sample data pools for things like users, IP addresses, actions that the users have taken, API endpoints, and incident types that get randomly chosen in order to create our log events. One function creates a normal payload, and a second one creates a dirty one. After the payloads are created, they're then pushed to AWS CloudWatch. Finally, an event summary is printed into CloudWatch for debugging and tracking purposes. All application logs are written to AWS CloudWatch. They go into a log group entitled CSCI E90/app logs, and from there into a log stream titled test stream. A subscription filter with a pattern of dash, meaning that it matches all logs, is configured on this log group, which also contains the ARN that Lambda uses in order to receive information from the log. This subscription filter triggers the Lambda function for every log event. This is what makes this system a fully event-driven configuration. Amazon CloudWatch delivers log events to our Lambda function. Each invocation of that function may contain multiple events, each one including a log group, log stream, individual messages, and the associated timestamps. The Lambda function decodes the payload and then iterates over each event independently. The sanitization logic is responsible for detecting and removing sensitive data from the messages before they are stored or analyzed, while still preserving enough context to make the logs operationally useful. The logic uses regular expression pattern matching in order to detect common forms of sensitive data. These include things like email addresses, IP addresses, and password fields. Regular expressions were chosen because the logs we receive from CloudWatch contain unstructured text, and regular expression pattern matching is very fast. When a sensitive value is detected, the original value is irreversibly replaced. A placeholder token is inserted, such as these listed here, like email redacted, IP redacted, etc. We also increment a counter in order to keep track of the number of redactions that occurred from a statistical perspective. This overall approach ensures that sensitive values cannot be reconstructed while keeping the type of exposure visible. This enables analytics to be able to distinguish what was redacted. The severity classification mechanism of our Lambda function translates our detection results into actionable intelligence. Instead of alerting on every redaction, the system tries to determine how serious was this exposure. The severity levels are classified as low, medium, high, and critical. A low level means that no sensitive data was detected, the information is only logged, and no alerts are sent. The medium level means that we found an email or IP address. We log that fact, but still make the information visible in our analytics, but once again, no alerts are sent. A high level means that at least one password was detected, and this triggers an SNS alert. The critical level means that an AWS access key or multiple passwords were detected. The AWS keys can enable infrastructure compromise, and multiple credentials might also indicate a systemic failure. The SNS alerts are only triggered on high and critical levels. When a high or critical level is encountered, this portion of our Lambda code creates the email that ultimately gets sent as an SNS alert. This email summarizes the events that were detected, the redactions that took place, and provides critical information to the analyst to understand what has occurred. For high and critical severity events, the Lambda function publishes an alert to an Amazon SNS topic. Each alert includes a unique alert ID, which allows us to correlate batches of events. The alert explains the overall severity and why it was classified as high or critical, and includes the triggering action, such as a failed login or API call. It also contains a summary listing all the severe events in that particular batch. No raw sensitive values are ever included in the alerts, only sanitized ones. This is an example of an email that was received with security alerts contained inside. We can see the overall severity of the event listed at the top and the reasons why the alerts were triggered. We get a breakdown of the severity level as well as a summary of the information in the alert. We provide an example of a sanitized event and then a redaction summary so we can understand exactly what was scrubbed from the logs. Finally, there's a listing of all the severe events in this particular batch. After the Lambda function has completed processing the events, log data is written to Amazon S3 buckets. Raw logs and sanitized logs are stored in separate buckets. The logs are written in the ND-JSON format, which stands for New Line Delimited JSON, making each entry its own object. This is done in order to optimize for the analytics we're performing. The data is partitioned in a year, month, day, Hive format, which improves query performance and reduces costs when using Athena. Separating the raw and sanitized data also enforces the principle of least privilege. In addition, each of the buckets is encrypted with an AWS KMS symmetric key. This is an example of a sanitized log written to our S3 bucket. AWS Glue is used to catalog the sanitized log data stored in S3. A Glue crawler scans the S3 bucket and automatically infers the schema. It also discovers partitions based on the directory structure. This metadata is stored in the Glue data catalog. Glue allows Athena and QuickSuite to query the data without manual schema management. Amazon Athena is used to query our sanitized logs directly from the S3 bucket using the standard query language, or SQL. With this approach, no database servers are required. Queries can be filtered by severity, action type, date, or a number of other parameters. This is an example of a query showing us the alert ID, severity level, and redaction stats for the last 10 log entries. Here's another example showing the total count of each one of the actions that triggered the events. An Athena view was created in order to flatten some of our nested data fields, such as the severity level. Using this view simplifies analytics and makes our QuickSuite integration more reliable. Amazon QuickSuite is used to visualize our sanitized log data. We first go in and create a data source, and then connect it as a data set to the view that we created previously in Amazon Athena. From there, we're able to perform analysis and create visuals with the data that is of interest to us. The visuals include parameters such as severity distribution, high-risk actions, and trends over time. Only sanitized data is exposed to QuickSuite. This allows the dashboards to be shared safely without exposing any sensitive information. The dashboards transform raw log data into actionable security insights. Once completed, they can be shared with interested stakeholders. Amazon CloudWatch logs also provide observability for our entire pipeline. They show incoming application logs as well as the execution of our Lambda function. We can put print statements in our Lambda code, and those are captured automatically by CloudWatch. This was done throughout the development process in order to track down errors, address permission issues, and troubleshoot schema problems. CloudWatch can also help to validate that the redaction and alerting process are working as expected. Here's an example of a CloudWatch execution log coming back from Lambda. With this level of detailed information, it's much easier to diagnose and troubleshoot problems in our code. Okay, I'm now going to run a live demo to show the pipeline in action. I'm going to start off by showing a couple of the current Athena queries and QuickSuite dashboards, so we'll be able to see that the information has changed after generating and processing the log information. Here in Athena, we'll run a simple SQL query that will give us the total number of records in our sanitized S3 bucket. We can see that that's 1,489. In QuickSuite, we can see in our severity distribution pie chart the total number of medium, high, and critical incidents. Okay, now we'll run the log generator. So this is what the log generator script looks like. We can see that we're going to generate 10 events, with roughly half of them being considered severe with data leakage occurring. So we go ahead and we run the script, and we'll see the 10 events that get pushed over to CloudWatch. Of those, 1, 2, 3, 4, 5 are actually considered severe with data leakage occurring. If we go into CloudWatch, and we go to our app logs and test stream, we can see the 10 events that were just created from our generator and all of the raw data that they contain. We can also go take a look at S3 and see the records in each one of the buckets. So this is our raw bucket and the hive structure we talked about earlier. And here's the raw log that our Lambda function pushed over to S3. In addition, we've also got the sanitized log with the sensitive data being redacted. CloudWatch also captures Lambda execution details, including the severity classification. So if we go back over to CloudWatch and look at our log sanitizer, we can see the information that came back from the Lambda function into CloudWatch. This information is very helpful for watching the execution of Lambda and tracking down any anomalies or bugs. Because we had several severe alerts, our SNS queries should have been triggered. And if we go and look at our email, we'll see the sample report that comes across detailing what occurred. We see the overall severity level is critical. We see that there were 3 critical alerts and 2 high in this batch. We see the types of incidents. We see a redaction summary. And then we see each one of the 5 severe events broken down in more detail in the report. Now, if we go back over to Athena, we can rerun our query asking for the total number of records, and we should see this increase by 10 for the 10 records that were just created. And that is in fact what we see. We have a couple other SQL queries here. This one shows us the total number of medium, high, and critical alerts. If we run this again, we'll see these numbers change slightly. This is an example that gives us the last 10 records that were written, just like we saw in CloudWatch. This is how we would look at a summary of the leaked information broken down by year, month, and day for each one of the types of categories. And then finally, we can see the actions that the user was taking that triggered the events. From here, we can go into our Quick Suite dashboards, and anytime we change one of these views, the information will be updated. So if we look at our severity distribution pie chart, we'll see that the counts of medium, high, and critical have moved up and match what we saw from Athena. We also have several other dashboards we created that show our data in different ways so we can perform further analysis and understand exactly what types of events are occurring, what kind of data is leaking, and how that information has changed over time. Because the information in these dashboards has been sanitized of any sensitive data, this information can be shared with all stakeholders. This demonstration shows the full end-to-end flow from log ingestion to alerting. And beyond that, it also provides analytics for further analysis. In conclusion, this project demonstrates a secure, real-time, event-driven log sanitization pipeline that was implemented using AWS CloudWatch and Lambda. We're able to take sensitive data and recognize patterns that need to be filtered out, redact that information, and remove it before writing the logs to long-term storage or performing analytics on it. Certain high-risk events generate SNS alerts that send email summaries, while low-risk events remain visible for analytical purposes. The combination of Glue, Athena, and Quick Suite enable us to query and visualize our events so we can identify trends over time. The system built is scalable, serverless, and entirely managed with AWS services. Thank you for watching.